Welcome to the second lesson of the 10th module, which is on springs part 2. In the previous lesson of this particular module, we have looked into the aspects of different kinds of springs. We have seen that what are the different types of springs and how they are used. Now, also we have discussed a special type of spring which we have called as helical springs, and as you have seen that helical spring is of two types. One is called as closed coil helical spring, another one is open coil helical springs. Now, in the previous lesson we have discussed about the closed coil helical springs, and we have looked into how the stresses and the deflections are induced in the springs when they are loaded. Now, in this particular lesson we are going to discuss about the closed coil helical springs. Hence, it is expected that once this particular lesson is completed, one should be in a position to understand the concept of stresses and deflection in open coil helical springs, and also one should be in a position to evaluate stresses and deflection in open coil helical springs which are subjected to loads. The scope of this particular lesson therefore includes, we will be recapitulating certain aspects of the previous lesson through the answers of the questions which were posed last time. We will be deriving a few formulae for evaluating stress and deflection in open coiled helical springs. Also, we will be looking into some examples for the evaluation of stress and deflection in open coiled helical springs. Now, before we go for the discussion on open coiled helical springs, let us look into the answers of the questions which were set last time. The first question was, what is meant by spring index? Now, if you remember, while discussing about the closed coil helical springs, we had discussed that how the stresses are induced, and we had seen that primarily the stresses which act on the springs are the direct shear stress and the a twisting moment, and both the forces they induce the shearing stress in the member. The direct shear force induce the shear stress, and the twisting moments also induce the shear stress, and thereby we get the total shear stress which we have designated as tau max, which is equals to 16 p r by pi d cube. And as you know these terms, that p is the axial load that is applied in the spring, r is the helix radius or the mean radius of the spring, and d is the diameter of the wear with which the spring is manufactured. And then we come across a term, is a bracketed term which we have designated as k, and if you look into this particular parameter k, k is equals to 1 plus 1 by twice c. Now, here if you look into 4 r is nothing but 2 into twice r, and twice r we can write as d, the mean diameter of the spring helix, and thereby we can write this particular parameter as 1 plus d by twice d. And as you can see here, we have written twice c, c therefore stands as capital D by small d, and this particular ratio capital D by small d we call this as spring index. Therefore, we define the spring index in this form, that it is the ratio of the nominal diameter of the spring or the helix diameter to the diameter of the wear with which the spring is made. So, this is called as spring index. Now, let us look into the second question, which was, what are the different types of stresses that closed coil helical springs are subjected to. Now, the closed coil helical springs, as we have seen, are subjected to two kinds of forces. One is the the direct force P and another is the twisting moment T. Now, as I had told you that in case of closed coil helical springs, they are wound in such a way that each helix is lying in one plane, and if that happens, then the force transferred to the spring is, or the wear, is the axial force P, which is transferred from the center to the center part of the wear, along with the twisting moment T, which is equals to P times R. Now, these two forces P and this twisting moment, they introduce stresses in the spring wear, and these stresses are tau 1, which is P by A, the direct stress, the direct shearing stress because of the shearing force P, which is equals to 4 P by pi d square, and because of this twisting moment T, which is equals to P times R, we get a shearing stress tau T, which is equals to 16 T by pi d cube. Now, as you know that T by J is equals to tau by rho, and tau is therefore T rho by J, and rho is d by 2 and J is pi d 4 by 32. So, if we substitute the value of rho and J, we get this as 16 T by pi d cube, and T being equals to P times R, the shearing stress tau T is equals to 16 P R by pi d cube. So, these are the two stresses that a closed coil helical spring is subjected to, which is 4 P by pi d square is the direct shear, and 16 P R by pi d cube is the shearing stress which is generating from the twisting moment T. And therefore, the maximum shearing stress that a wear of the closed coil helical spring will be subjected to is equals to 16 P R by pi d cube times 1 plus d by 4 R, which we have designated as K. So, this is the value of the stress that a closed coil helical spring is subjected to. Now, the last question which we had was, how do you define the stiffness of a closed coil helical spring? Now, to answer this question, let us look into the expression for the deflection that we had derived. If you remember, for the closed coil helical spring, we had the value of the deflection delta because of the action of the axial load P was 64 P R cube N by G d to the power 4, where these terms again have the usual meaning, like P is the axial force, R is the radius of the helix of the spring, N is the number of turn of the spring coil, G is the shear modulus, and D is the diameter of the wear. Now, if we write this particular expression in a little different way, if we represent P as a function of the displacement delta, then we get the expression P as equals to G d 4 divided by 64 R cube N times delta. Now, generally as we have seen, we define stiffness as the force required to produce unit displacement. Now, here if we replace delta as unit, the force we require to produce this unit displacement, we define that particular the coefficient as the stiffness. So, if we write down this expression as P equals to K S K suffix S times delta, when delta is equals to 1, the force which we get is equal to the stiffness of the spring. So, thereby the spring stiffness K S we define as this G d to the power 4 by 64 R cube N. In fact, you had seen that we had talked about the spring index, which was also of the same form, that P by delta, which was equals to G d 4 by 64 R cube N. So, this is what we define as the spring stiffness. So, these were the answers of the questions which were posed last time. Now, having looked into this, let us look into the aspects of the open coil helical spring. Now, as I had told you last time, that helical springs are commonly used to absorb shocks, and these are used in railway buffers and many other areas. And helical springs which has a helix in this form are of two types. One is called as closed coil helical spring and another one is called open coil helical spring. Now, you can look into these springs which are having two different wounds. Now, you know, this is a spring in which you have the wear are wound in such a way they are at a very close distance, the pitch between the two wounds are very close. So, this resembles to a great extent to the closed coil helical spring. In fact, in reality these pitch are much less, and in fact they are almost in the same horizontal plane. Whereas, if you look into this particular spring where the pitch between the two helix is substantially large in comparison to the previous one, and here they do not lie in the same plane. If we consider one such helix from one point to the other point, they do not lie in the same plane. The plane is inclined with respect to the horizontal one, and this is basically is the difference between the closed coil and the open coil helical spring, and thereby there is difference in the load transfer mechanism as well. Now, when we look into this closed coil and open coil helical springs, we find that there is a difference in the load transfer mechanism. In case of closed coil springs, we have seen what are the forces it undergoes, or it I mean what are the forces it is subjected to. In case of open coil springs, now we will look into that what are the forces these will be subjected to. Thereby, we define the open coil helical spring as the wares with which open coil helical springs are formed are wound, so that each turn of the spring is not lying in one plane, as the pitch of the coils is larger. As you can see over here that the pitch is the distance between these two helix. Now, this we have defined as small p. Now, in case of closed coil spring, this p is very small, so that virtually this one of the wound lies in the same plane, whereas in case of open coiled one, they do not lie in the same plane, and the helix has an angle which is inclined with respect to the horizontal plane, and thereby when we talk about the load transfer mechanism, you will find the forces that a closed coil helical spring will be subjected to is different from the I mean open coil spring will be subjected to is different from the closed one. So, let us look into then that what are the forces that the closed the open coil helical springs are subjected to. Now, as we had seen in case of closed coil springs, that a spring is subjected to load P, maybe the top is held against some supports. Now, we define these are the helix of this spring, and we define this distance between the two helix as P. Now, if they are in the same plane, because from this end to this end, if it comes up to this is one circular form, and thereby if r is the radius of this mean radius of this spring, then the length of this particular plane will be twice pi r. Now, if they are in the same plane, the length of that wound will be twice pi r, but since there is a inclination, now there is the helix is inclined with respect to the horizontal plane because of the larger pitch, then the length is going to be larger than the twice pi r. Now, if we look into this particular triangle, that let us define that this distance as the pitch p, and the horizontal distance is the distance twice pi r when the wound lies in the same plane. Now, since it has an inclination, let us assume that the length gets extended and the helix angle between these two planes is equals to alpha. So, from this particular triangle we can say tan alpha is equals to P divided by twice pi r, and that is how we define the helix angle alpha with which this particular wear is wound. Now, if we look into the forces that this will be subjected to, now first if I transfer this axial force P to the straight coil which is in the one plane, will be subjected to a direct force P and a twisting moment P times r, the vectorial direction of which will be this we had seen last time. Now, since this is the position of the open coil spring now because of the inclined plane, now if we resolve these forces along this and perpendicular to this direction, then what all we get. Now, so what we have is this is the direction of the axis of the spring wear, and the force which is acting is in this vertical direction. So, perpendicular to this makes an angle alpha. So, we get the component as P cos alpha, and along the axis will be P sin alpha. Now, the component which is acting as P sin alpha along the axis of the wear, that will give us a tensile pull, and the force which is normal to this cross section which is P cos alpha will give us a shearing force V. So, the force P now contributes to two actions. One is the tensile pull, which is T, which is given by P sin alpha, and the shearing force which is acting perpendicular to it gives rise to V, which is P cos alpha. So, these are the two forces that it will be subjected to because of the load P. Now, P also has introduced a twisting moment which is P into R, and the vectorial direction of which is this. Now, if we take the component of that moment along this position of the spring coil and perpendicular to it, along the member, when we take the component of this moment which is P R cos alpha, we will be introducing a twisting moment in the wear. So, this is the amount of or the action of the moment which we have defined as MT, which is equals to P R cos alpha. And if we take this vectorial direction moment, the component along the perpendicular to this wear axis, this is equals to P R sin alpha, and this is going to cause a moment. So, one we have the moment which is a twisting moment in the wear, and the other one is going to cause a bending moment, because the vectorial direction is perpendicular to the wear axis, and the moment which is acting is a bending moment in the wear. So, because of the twisting moment that it was acting in that plane where the wound is perfectly in the plane, there it was a twisting moment, and this twisting moment has two components. One is along the member axis, which is causing a twisting moment in the wear, and other one, the vectorial direction is perpendicular to the wear axis, which is a bending moment to the wear. So, now as you can see that the force P has two components, one is T, another one is V. T is the direct tension that is causing in the wear, and V is the shear that is being caused in the wear because of P, which are P sin alpha and P cos alpha. And the twisting moment P into R will have two components, one is causing twisting moment which is equals to P R cos alpha, and another one is causing a bending moment which is equals to P R sin alpha. So, as you can see, then the axial force P will introduce four force components in the open coil springs, and they are the tensile pull in the wear, a shearing force V, the twisting moment MT, and a bending moment MB. And the stresses corresponding to each of these forces will be, because of the bending moment MB, there will be normal stress, and which is MB, as you know, sigma is equals to M y by I, this is the bending normal stress. Then there will be normal stress because of the axial tension T, T divided by cross sectional area will give the normal stress. Then because of the direct shear V, we will have the shear stress, which we call as a B divided by the cross sectional area, and the shear stress because of the twisting moment MT will be, as we know, that T by J is equals to tau by rho. So, tau is equals to T rho by J will introduce a shearing stress. So, as you can see that the axial force which is acting in the open coil helical springs will be introducing four components of the forces, which is the tensile pull along the wear, a shearing force in the transverse direction, then a twisting moment in the wear, and a bending moment in the wear. And all these four force components of the stress resultants will introduce stresses in the member, which are the normal stresses and the shear stresses. Now, these two normal stresses which are resulting from the bending moment and the direct tensile pull, we can have a combined normal stress, and the shearing stresses which are resulting from the twisting moment and the transverse shear, we can have a resulting shear, and from the normal and the shearing stress we can compute the resulting value of the maximum normal stress and the maximum shear stress using Mohr circle or transformation equations. So, these are the stresses that we have, normal stress due to bending, which is equals to because it is a circular in cross section, and as I have told you that sigma is equals to M y by I, and as you know, for circular cross section I is equals to pi d4 by 64 and y is d by 2. So, this is M d by 2 divided by pi d4 by 64, and this gives rise to 32 mb by pi d cube, and mb as you have seen is equals to p r sin alpha. So, that if you substitute, this gives you 32 p r sin alpha by pi d cube. Now, normal stress due to axial tension is equals to the tensile pull divided by the cross sectional area, and tensile pull as we have seen is equals to P sin alpha, and cross sectional area is pi d square by 4. So, this is 4 P sin alpha by pi d square. Now, the shear stress due to transverse shear, as you have seen that the transverse shear is equals to V, which is P cos alpha, and the maximum shear which we get at the diameter of the circular section, that is equals to 4/3 V by A, and that is equals to A, if we write as pi d square by 4, gives rise to 16 P cos alpha by 3 pi d square. So, this is the shear stress because of the transverse shear V, and then shearing stress due to the torsion, which is, as I said, that T by J is equals to tau by rho. So, tau is equals to T rho by J, and rho you know is d by 2 and J is pi d 4 by 32. So, that gives rise to 16 the twisting moment by pi d cube, and twisting moment we had seen as pi P r cos alpha. So, this is 16 P r cos alpha by pi d cube. So, these are the 4 stresses that we have, and if we combine these 2 stresses, the normal stress with the normal stress, we will have the resulting normal stress which we call sigma max, and then from these 2 shear stresses we will have the tau max, and this sigma max and tau max we can make use of Mohs circle to find out that what will be the maximum and the minimum principal stresses and the maximum shear stress because of these 2 actions. So, here is indicated that the maximum normal stress is equals to 32 P r sin alpha by pi d cube. This is because of the bending, and this is because of the axial tensile pull. So, if we combine these 2, we get this as 32 P r sin alpha by pi d cube, which is because of the bending part, times 1 plus d by 8 r. Now, if you look into this particular ratio d divided by 8 r means it is 4 times twice r is capital diameter, the nominal diameter of the spring. So, this is d by 4 times capital D. Now, this particular ratio is very small in comparison to 1. Now, this indicates that the normal stress because of the bending is much higher than the normal stress because of the axial tensile pull. So, the contribution of the axial tensile pull in the normal stress is very insignificant in comparison to the normal stress that is being produced by the bending. Likewise, if we combine the shear stresses, this is the shear stress because of the twisting moment, and this is the shear stress which we get because of the transverse shear V, and if we combine these together, then 16 P r cos alpha by pi d cube is the shearing stress because of the twisting moment. This gives 1 plus d by 3 r. Again, here if you look into this, that this ratio is very small in comparison to 1, and thereby the contribution in the shear stress because of the twisting moment is much higher than the contribution of the direct shear stress because of the transverse shear V. So, in fact, subsequently we will look into for evaluation of the deflection of the spring because of the axial load. We have computed the value of the deflection primarily from the actions of the twisting moment and because of the bending moment, because the actions of the axial tensile pull or the transverse shear force is very small in comparison to the twisting or the bending. So, once we have the maximum value of the sigma, which we have called this as sigma max, which is the sum of the 2 normal stresses, and sum of the 2 shear stresses we have called them as tau max. So, considering this sigma max and tau max value, we can compute the maximum normal stress sigma 1, which is equals to sigma max by 2 plus root of sigma max by 2 square plus tau max square, and this expression as we had seen earlier that we can obtain from the transformation equations, or we can evaluate from the Mohs cycle, that in the Mohs cycle we plot the sigma and tau, because sigma y here is 0, and then if we join them together, then we get this as sigma by 2 and this as the radius is sigma by 2 square plus tau square, and this will give us the value of sigma 1, and this particular part is the maximum shear stress. So, this is the total is the maximum normal stress, and this under root part is the maximum shear stress that will be generated in the spring wear. Now, if we neglect the parts, as I have said that the contribution of the axial tensile pull or the transverse shear is very insignificant in comparison to the stresses that is induced because of the bending and the twisting moment. Now, if we disregard the stresses because of the direct tensile pull and the shear stress due to the transverse shear, then the value of the stress, the maximum normal stress sigma 1, we can write as this is the shear stress which the normal stress which is getting generated because of the bending, which is 16 PR sin alpha by pi d cube, half of that, that is 32 PR sin alpha by pi d cube divided by 2 gives us 16 PR sin alpha by pi d cube, and this is sigma by 2 square plus tau square, and this tau is getting generated from the twisting moment, which is PR cos alpha. And if we take out this 16 PR by pi d cube from the root, we are left with sin square alpha plus cos square alpha, which is equals to 1. So, this gives us a value of 16 PR by pi d cube sin alpha plus 1. This is the value of the maximum normal stress, and as you know that this particular part gives us the value of the maximum shearing stress. So, the maximum shearing stress is equals to 16 PR by pi d cube. So, these are the two values of maximum normal stress and the maximum shear stress when we disregard the tensile stress because of the direct tension and the shearing stress due to the transverse shear. So, those two direct stresses if we disregard, if we take only the stress because of the bending and the stress because of the twisting moment, then we get the values of the maximum normal stress and the maximum shearing stress. Well, having looked into the stresses, let us look into the aspects of the deflection that it will be occurring in a open coil helical spring. Now, as we had seen that in case of closed coil helical spring, the d delta is equals to r times d theta. If you remember that the closed coil helical springs, when it was subjected to the axial pull, we had evaluated that what is the vertical component of the deflection that it is undergoing because of the twisting moment, and there of course, we had disregarded the effect of the transverse shear. We had considered the deflection because of the twisting moment, and we had shown you that because of the twisting moment it undergoes a vertical deflection which is equals to r times d theta, where d theta is the rotation that is being generated because of the twisting moment t, which is p times r. Now, if we take that as our basis to evaluate the deflection in open coil spring, then it is going to be like this, that d delta as we have seen for a closed coil as r d theta. Now, the difference between the closed coil and the open coil as we had seen is this helix angle, that here you have that angle is very large, where the length 2 pi r virtually becomes the length which is this. Now, so it has an inclination alpha. So, the deflection which we had, which is equals to r d theta, will have in this particular open coil as equals to r d theta cos alpha, which is because of the twisting moment t, and because of the bending moment it will have r d theta sin alpha. So, now as we have seen that d theta is the twisting moment, the rotation of the spring because of the twisting moment mt, which is equals to mt ds by gj. ds is the length along the spring wear. Now, mt is the twisting moment which we have seen as pr cos alpha. Now, if we substitute now for d theta as mt ds by gj, then we have mt r by gj times cos alpha. Now, here this rotation d theta is for a small length ds. Now, if we calculate, so this is the small increment in the vertical deflection d delta 1, which will be caused by this small element ds. So, if we like to get the whole deflection over the entire spring, which is integral of d delta 1 over 0 to L, then we will have ds as integral 0 to L ds, which is the length. Now, when the wear is wound in one plane, the length of the wear is equals to twice pi r. Now, because of this inclination, it has taken this particular length. Now, this length let us call this as say L dashed. So, L dashed cos alpha is equals to twice pi r. So, L dash therefore is equals to twice pi r by cos alpha. Now, if there are n number of turns, then the total length of the spring will be twice pi r into n, and that divided by the cos alpha will give us the final length of the spring. And so, here we have substituted then for integral ds as L, as you can see in this expression, which is mt r L cos alpha by g j, and for mt we have substituted as p r cos alpha, which gives us p r square cos square alpha, and for L we have substituted this as twice pi r n by cos alpha. So, once we substitute, and j is pi d 4 by 32. So, if we simplify this particular expression, this comes as 64 p r cube n cos alpha by g d to the power 4. So, this is the value of delta 1, the deflection that the spring undergoes because of the twisting moment mt, which is equals to p r cos alpha. Now, because of the bending moment which we have, which is equals to p r sin alpha, we will have the component of the vertical direction, or the deflection that will cause the deflection in the vertical direction, which is equals to r d theta sin alpha. Now, in this particular case, as we know that m by I is equals to sigma by y is equals to E by r, and 1 by r is nothing but equals to curvature, which is equals to d theta ds. So, d theta ds equals to m by E I, where m suffix b is the bending moment, and therefore, d theta is equals to m b ds by E I. So, in r d theta by sin r d theta times sin alpha, there if we replace d theta as m b ds by E I, and if we integrate that, then so d delta 2 becomes p r square sin square alpha ds by E I. So, if we integrate this, we get delta 2, and this integral ds will give us the length, and length as usual again it will be twice pi r n divided by cos alpha, and that if we substitute, we get the value of delta 2 as equals to 128 p r cube n sin square alpha by E d 4 cos alpha. And as you know that the value of the bending moment m is equals to p r sin alpha, and here we had one sin alpha. So, that gives you sin square alpha, and I is pi d 4 by 64. So, that is when multiplied with this becomes 128 p r cube n sin square alpha by E d to the power 4. So, this is the value of the delta 2 that we have, and if we combine this with the delta 1 that we have from the twisting moment, we get the total deflection that will be caused in the spring because of the twisting moment and the bending moment. So, these are the two expressions that we have obtained, that for delta 1 is because of the twisting moment mt, and delta 2 is because of the bending moment mb. And note that we have disregarded the deflection in the spring because of the axial tensile pull and the transverse shear, as we have seen that the effect of the tensile pull and the transverse shear is very small in comparison to the twisting moment and the bending moment, and accordingly we have disregarded those components, and we have computed the value of the deflection exclusively for the twisting moment and the bending moment. And as we can see that the delta 1, the deflection because of the twisting moment is this expression, which is 64 p r cube n cos alpha by g d to the power 4, and delta 2 is the deflection because of the bending moment, which is 128 p r cube n sin square alpha by E d to the power 4 times cos alpha. So, the total deflection then will be sum of these two, which is delta 1 plus delta 2, and that if we combine, you get an expression like this, that 64 p r cube n d to the power 4 cos alpha times cos square alpha by g plus 2 sin square alpha by E, and you know the meaning of all the terms. P is the axial pull, r is the mean radius of the spring coil, n is the number of turns, d is the diameter of the wire with which the spring is formed, g is the shear modulus, and E is the modulus of elasticity, and alpha, as you know, is the helix angle, which is tan inverse p by twice pi r. Well, now because of this load, not only the spring will undergo a deflection. Now, what will happen is that if we hold this particular spring and the load is applied, this will be subjected to a deflection, also it will undergo angular rotation. If it is held at this position and if you apply this load, it will undergo angular rotation. So, we need to find out the angular rotation. Now, because of this angular rotation, because of the twisting, it will try to increase this wound and bending will try to reduce this wound. So, we need to find out the value of the theta, the angular rotation, and due to twisting moment, this twist the rotation theta 1 is given by this expression 64 p r square n sin alpha by g d to the power 4, and due to bending moment we will have the rotation which is 128 p r square n sin alpha by e d to the power 4. Now, algebraically we add them up theta 1 plus theta 2, but as you have noticed that because of the twisting moment, the angular rotation will have a clockwise movement which will try to increase the number of wounds, and in case of bending it will have an anticlockwise movement, and that will try to unwound the spring. So, the final rotation, angular rotation that we will have with respect to the top will be the difference between the two, which is theta 1 minus theta 2, and if we try to find out the final theta, this is the difference between these two, which is 64 p r square n by d to the power 4 sin alpha times 1 by g minus 2 by e. Now, because of this angular rotation, it is expected that there is going to be increase in the number of wounds. When the angular rotation is there, from the original number of wounds there will may be increase in the number of wounds, and if we call this as n dashed, then twice pi n dashed is the number the rotation that it undergoes in a deformed state, and earlier it was twice pi n. So, the increase is twice pi n dash minus twice pi n, from which we can compute that increase in the number of wounds, which is n dashed, is equals to theta by twice pi plus n. So, n is the number of wounds that it had originally, and because of the application of the load P, this particular spring has undergone an angular rotation theta. So, that will give us the number of increase in the wound, which is n dashed, is equals to theta by twice pi plus the number of wound n which we had originally, or the difference could be n dash minus n, which is equals to theta by twice pi. This will give us the number of wounds increased because of the axial load P which is applied in the spring. Well, so these are the stresses and the deflection and the rotation that an open coil spring is subjected to, and you have now seen the difference between the closed coil helical spring and the open coil helical spring, and you have seen the load transfer mechanism into these two types of system. In case of closed coil helical spring, the wound is such that virtually the whole one helix lies in one plane, and thereby it is subjected to a direct shear and a twisting moment, which is P times R. Whereas, in case of open coil helical spring, because the helix is in an angle with respect to the horizontal plane, and thereby the axial force which is acting through the center of the helix introduces 4 components of the forces, which are the axial tensile pull in the wear, the transverse shear in the wear, the twisting moment and a bending moment, and these 4 stress resultants cause the corresponding stresses, which we have seen that individual normal and the shearing stresses, and from those individual normal and shearing stresses we can compute the maximum value of the normal stress and the shearing stress that the wear will be subjected to. And also consequently, because of the application of the load, we have seen that how the spring undergoes deflection and the angular rotation, which can be computed, which can increase the number of wounds or decrease the number of wounds depending on the application of the load. Now, let us look into some examples wherein we can make use of these formulae for evaluating the stresses in open coil helical spring. Now, the first example is that an open coil helical spring has a mean radius of 150 millimeter. So, the value of R, capital R, is 150 millimeter, and it has 20 coils. So, the number of turns, capital N, is 20, and the diameter of the wear is 20 millimeter at a pitch of 100 millimeter. This is the small p. So, you will have to find out the maximum stresses in the wear when the spring is subjected to an axial load of 200 Newton. Also, you will have to find the vertical deflection and increase in the number of coils. The value of E is given as 200 gigapascal and value of G, the shear modulus, as 80 gigapascal. Now, let us look into then that what are the values given and how do you compute rest of the stresses. Now, the values given are capital R as 150 millimeter, number of coils N is 20, the D, the diameter of the wire, is 20 millimeter and the pitch of the helix is 100 millimeter. Capital P, the load which is acting, is 200 Newton, value of E is 200 GPa and G is 80 GPa. Now, the first thing as we do is we calculate the value of alpha, the helix angle, and as you know, alpha will be given by this angle, which is, this is P and this is twice pi r, the straight length, and thereby tan alpha is equals to P by twice pi r. P is 100, R, capital R is 150. So, this gives us a value of alpha as 6.06 degree. So, this is the helix angle with which the wire is inclined with respect to the horizontal plane. Now, once we know the value of alpha, then we can compute the four force components that will be acting in the spring, which is twisting moment MT is equals to PR cos alpha, which we have seen already. The bending moment MB is equals to PR sin alpha. The axial tensile force that will be acting in the spring is equals to, or spring wear, is equals to P sin alpha, and the transverse shear V is equals to P cos alpha. So, the value of P is given as 200, R is 150 and cos of 6.06. So, this gives us a value of 29,830 Newton millimeter. So, much of twisting moment, and the bending moment is likewise we have 200 into 150 into sin of 6.06 degree, which is equals to 3170 Newton millimeter. So, so much is the bending moment. Now, the value of the axial tensile pull T is equals to P sin alpha, which is equals to 200 to sin of 6.06 degree, which is equals to 21.11 Newton, and the transverse shear V is equals to 200 cos of this, which is equals to 198.8 Newton. So, these are the four force components which we have, which the spring wear is subjected to. Now, let us compute the value of the stresses corresponding to each of these force quantities. Now, the values of the stress, the bending stress sigma, as you know, is equals to 32 the bending moment by pi d cube, and bending moment as we have seen is equals to 3170 Newton millimeter and D is 20 millimeter. So, this gives us a stress of 4.04 megapascal, and also the stress sigma tensile, the normal tensile stress, or the normal stress which is getting generated because of the tensile pull is equals to T by A, and the tensile pull which we have seen is equals to 21.11 Newton divided by pi d square by 4. So, D is 20. This gives us a value of 0.07 megapascal. Now, here you can look into these numerical values, that the normal stress which is getting generated because of the axial pull is very small in comparison to the normal stress that got generated because of the bending moment M. So, this is insignificant in comparison to this bending stress. Now, let us look into the value of the shearing stress that is getting generated because of the twisting moment and the direct shear. Now, because of the twisting moment, if we call that as tau 1, which is equals to 16 mt by pi d cube, mt is the twisting moment, and that we have seen as 29,830 and D is 20. This gives us a value of 19 megapascal as the shearing stress because of the twisting moment, and the shearing stress because of the direct shear V is equals to 4/3 of V by A. This is the maximum stress, as we have observed that when we have computed the shear stress in a circular cross section, we had observed that the maximum stress occurs at the center, and the value of the maximum shearing stress is equals to 4/3 V by A, and that is what has been taken here, which is equals to 4/3 V by A, and V as we have seen is equals to 198.9 and area is pi d square by 4. So, this gives us a value of 0.84 MPa. Now, if you look into this particular stress that is getting generated because of the transverse shear V is very small in comparison to the shear stress which is getting generated because of the twisting moment MT. So, this is almost insignificant in comparison to the shear stress tau 1. Also, if you look into the other values, that the stresses which have generated because of the bending and the direct axial, there also is much less in comparison to the shearing stress that is getting generated because of the twisting moment. Of course, this depends on the helix angle as well. If the angle changes, alpha angle varies, then there will be change in these stresses, as we have seen. Now, so the normal stress, the total normal stress which we have is the normal stress because of the bending and the normal stress because of the tensile pull, and this comes as equals to 4.11 megapascal. And the shearing stress, the total shearing stress that we have, tau, is equals to tau 1 plus tau 2, which is equals to 19 plus 0.84. This gives us a value of 19.84 megapascal. This is the value of the shearing stress that are getting generated because of the twisting moment and the transverse shear. Now, once we have this value of sigma and tau, we can substitute these values in this expression, or we can plot them in the Mohr circle to get the value of the maximum normal stress sigma 1, which is equals to sigma by 2 plus root of sigma by 2 square plus tau square, and sigma being 4.11 and tau being 19.84. So, this is the expression for evaluating the normal stress, and if we compute the value of the normal stress comes as 22 megapascal, and the shearing stress, the maximum shearing stress, which is given by this particular expression, which is root of 2.0 root of sigma by 2 square plus tau square, which is 2.055 square plus 19.84 square, and this gives us a value of 19.95 megapascal. So, this is the maximum normal stress, and this is the maximum shear stress that the spring will be subjected to. Now, let us look into the value of the deflection that the spring will be subjected to because of the action of this load which is acting in the spring. Now, as we have seen that the deflection expression for deflection delta is equals to 64 p r cube n by d to the power 4 cos alpha into cos square alpha by g plus 2 sin square alpha by e. And as we have seen, the value of alpha we have computed as 6.06 degree, and other values are given. In the number of turn is given as 20, capital R is 150, and the load P is equals to 200 Newton. So, and G, the shear modulus, equals to 80 gigapascal. So, that is converted into megapascal, and this is E is 200 gigapascal, which is 200 into 10 to the power 3 megapascal. So, that everything is in terms of Newton and millimeter, in Newton and millimeter. Therefore, this value of delta is in millimeter, so much of millimeter. So, if we substitute these values over here, P, R, N, D, alpha and G, then the value of the delta, the deflection which we get, is equals to 68 millimeter. So, because of the application of the load P, which is acting in this open coil spring P, this is causing a deflection of 68 millimeter. Now, as we have observed that not only this will undergo deflection, but it will undergo angular rotation as well. Now, the value of the angular rotation, as we have seen, is the theta equals to 64 p r square n by d to the power 4, which is sin multiplied by sin alpha by 1 by g minus 2 by E. And if we substitute these values, 64 p is 200, r is 150 square multiplied by n, which is 20, and 20 to the power 4, d to the power 4 is 20 to the power 4, sin of 6.06 degree. Then 1 by g, g is 80 into 10 to the power 3 minus 2 into 200 into 10 to the power 3. So, this expression once you simplify, you will find that the value of theta is equals to 0.0095, and as we had seen that n dashed, the increase in the number of, or total number of coils, is equals to theta by twice pi plus n. N is the number of turns that we had initially, and n dashed is the number of turns that have been introduced after this angular rotation. So, the increase in the number of turns is n dash minus n, which is equals to theta by twice pi, and this is what has been computed over here. Theta by twice pi gives us a value of 0.0015. So, that is the amount or the number of turns that are increased because of the axial pull P that is acting in the spring, and that is the value of n dash minus n. N is the number of turn which we had initially, and n dash are the number of turns that is getting introduced now because of the angular rotation theta, which is given by theta by twice pi. Well, let us look into another example of this open coil helical spring, that in an open coil helical spring of 10 coils, the stresses due to bending and torsion are 100 MPa and 110 MPa because of the bending and the torsion is given respectively. Now, when the spring is loaded axially, now the mean diameter of the coil is 8 times the wear diameter. The mean diameter is capital D of the spring is equals to 8 times the wear diameter, that is 8 times small d. To find the maximum allowable axial load, the capital P is to be evaluated and the wear diameter small d for a maximum extension of 18 millimeter. The value of delta is given. You will have to find out capital P and small d. The value of E and G are given as 200 gigapascal and 80 gigapascal. Now, if we look into these values given, and the number of coils are 10. Now, the permissible bending stress is equals to 100, that means the normal stress that is getting generated because of the bending. The permissible shear stress because of the twisting moment is 110 megapascal, and capital D, the nominal diameter of the spring, is equals to 8 times d, and delta, the deflection, is equals to 18 millimeter. E is given as 200 GPa, G as 80 GPa. You will have to compute the value of P and capital P and small d. Now, as we have seen that the bending moment M is equals to P r sin alpha, and that if we write now, stress sigma is equals to M y by I, and that is what has been indicated over here. Y is d by 2, I is pi d 4 by 64. Therefore, this is equals to 32 M by pi d cube, and thereby M is equals to pi d cube by 32 multiplied by sigma. So, M, which is P r sin alpha, is equals to pi d cube by 32 multiplied by sigma, and since d, capital D is 8 d, so capital R is 4 d. So, P times 4 d multiplied by sin alpha is equals to pi d cube by 32 multiplied by the sigma bending, the stress is given as 100 MPa, is 100. So, this gives us a value of P sin alpha is equals to 2.45 d square. Now, the twisting moment MT is equals to P r cos alpha, and again as you know that tau is equals to T rho by J, and rho is d by 2, J is pi d 4 by 32. So, this is equals to 16 T by pi d cube, and therefore, the twisting moment is equals to pi d cube by 16 times tau, and that is what is indicated over here, that twisting moment is P r cos alpha and also is equals to pi d cube by 16 times tau, and tau is given as 110 MPa permissible tau, and R as we have seen is equals to 4 d. So, if we simplify this, we get that P cos alpha is equals to 5.4 d square. Now, if we take the ratio of these two, P sin alpha by P cos alpha is equals to 2.45 by 5.4. So, that gives us a value of alpha, which is tan inverse 2.45 by 5.4, which is equals to 24.4 degree, which is the helix angle. And this, if we substitute over here alpha, we get an expression for P, which is equals to 5.93 d square. Also, now that we know the limiting deflection, which is equals to 18 millimeter, and the value of the deflection delta is given by this 1664 P r cube n by d to the power 4 cos alpha times cos square alpha by G plus 2 sin square alpha by E, and if we substitute these values of G, E and alpha, n is given as 10 and R as you know is equals to 4 d, we get P as equals to 33.03 d. Now, we have seen that P is equals to 5.93 d square, and now we get P as equals to 33.03 d from the limiting deflection delta. Now, if we equate these two, from this we get the value of d, the diameter of the wear as 5.57 millimeter, and if we substitute this value of d in this particular expression, we can get the value of P, which is equals to 184 Newton. So, these are the values of the allowable P and the diameter of the wear that is to be used for forming the spring. Now, there is another example that find the mean diameter of an open coil spring of helix angle 30 degree to give a vertical deflection of 25 millimeter and an angular rotation of the loaded end of 0.02 radian under an axial load of 40 Newton. The spring is made of a wire of 6 millimeter diameter and the value of E and G are given as 280 gigapascal respectively. Now, if we look into this, the alpha value is given, the deflection delta is given as 25, theta is given over here and P is equals to 40 Newton, the value of small d is 6 millimeter. Now, you will have to find out that what will be the mean diameter capital D or the radius mean radius r. Now, if we look into these values, that delta is given as 64 p r cube n by d to the power 4 cos alpha times cos square alpha by g plus 2 sin square alpha by E, and since the limiting delta is 25 millimeter, if we substitute the values except this r and n, I mean n also is okay, r and n is not known, then we get the value of r cube n as equals to 923.4 into 10 to the power 3. Now, we know the limiting angular rotation is equals to 0.02 radian. So, if we substitute these values and then accept r and n, we get the value of r square n is equals to 8.1 10 to the power 3. Now, if we divide this to this r cube n by r square n, we get the value of r, which is equals to 114 millimeter. So, the diameter is equals to 228 millimeter for this particular spring. Now, to summarize then, that in this particular lesson we have looked into some aspects of the previous lessons, and also we have derived the formulae for evaluating the stresses and deflection in open coil helical springs. Also, we have looked into the examples for evaluating stresses and deflection in open coil helical spring. Now, this particular lesson is the last lesson of this particular module, and as you have seen in this particular module of spring, we had two lessons. In the first lesson, we had introduced the concept of the spring, we had looked into the different types of springs, and we had discussed several aspects of the stresses and deflection in closed coil springs. And in this particular lesson, which is the second lesson of this particular module, we have looked into the stresses and deflection in open coil helical springs. And these are the two aspects that we have seen in lesson 1 and lesson 2, and these are the questions which are set for you, that what is spring constant and what are the differences between closed coil and open coil helical springs, what are the forces the open coil helical springs are subjected to. Look into these questions, and if you go through the this particular module, the two lessons of this module, you will get the answers of these questions. Thank you very much.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape, and IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today.